I'm going to solve now exponential equations by using the log function. So, how is this different from what we've done in the past? The differences here is I've noticed the base here is a 3, the base here is a 5. I cannot write this in base 3. Well, I could, but it's going to be a lot of work. In fact, the work that it would take to make these bases equal is then the same result that I'm about to produce by doing a different method. So the difference here is that here I recognize everything could be written with a base of 5, but here I recognize that trying to do that is going to be laborious. So that's not going to be the approach. What is going to be the approach? Is so I'm right when I start with. What I recognize again is that this is the variable. The variable is sitting as an exponent. And here in this example, the exponent, well, again, the variable, and the way I got it down is just to recognize that I needed to make the exponents equal to each other in order to make the whole thing equal to each other. Okay, but the same approach. The question becomes, if my variable's in the exponent, how do I get it down? Well, what I do have is this rule that says, look, if I have natural log of, say, a to the b, this is equivalent to b natural log of a. That's the power rule of logs. In other words, if I have an exponent here, but I have a log, I can bring that exponent down. So the approach here will be the following. I'm going to take the natural log of both sides. Now, could I take the log of both sides? You can take the log, any log. The log itself is irrelevant, except for one little thing. We're going to do two things. We're going to find the exact answer, and we're going to find the decimal equivalent. Now, for the decimal equivalent, if you're going to use a calculator, natural log and log base 10 are the two that are clearly visible on most, well, all scientific calculators. Depending on scientific calculator, you might have other bases available to you, but these two are the prominent ones. So since it doesn't really matter which one I use, it's going to come out exactly the same, I might as well just take the natural log of both sides, and then I'm going to apply the power rule and bring this variable down. Now, what do I have? This is a linear equation. This is linear. How do I know it's linear? Constant times a variable equals a constant. Natural log of 5 is a constant. Natural log of 3 is a constant. So this is no different than trying to solve something like this. 3x equals 7. I would take and divide both sides by 3 to solve this. Well, nothing different. Again, notice I brought this down. I'm going to leave this alone. I'm going to write this over again. So I won't write over the result. But in this step, what I need to do is divide by natural log of 3. Sorry, not handwriting, but I was writing another something else and I changed my mind halfway. Natural log of 3 divided by natural 3, that's a 1. And so what I have here now is my answer is x equals to, natural log of 5 over natural log of 3. So as far as the answer is concerned, the answer is going to be this. And this is the exact answer. Now, as soon as you go to your calculator, you're going to get an approximation. So let's say I did want an approximation. So all I'm going to do is find my log. It doesn't really matter. Does it matter if you use natural log or log? No, the answer is going to be exactly the same no matter what you use. So I'm going to just click natural log, divide that by natural log of 3. And then I have also what x is approximately. So x approximately is 1.46. And I'll go to 4 decimal places. That'll be 1.46, 4, and then since this 9 is here, and this is next one next to it is a 7, I need to bring this up, and that will become a 0, but then I need to bring the other one up. So it all of a sudden becomes 1.4650. So again, this is the fourth decimal place, but this one is bigger than 5, so it reaches this one by 1. But when I do that, that becomes a 10, which causes this next one to increase by 1. And there it is approximately to 4 decimal places. But this is the exact answer. Let's look at another one. Solve this by finding the exact answer and decimal equivalent. So what has changed? Not much, not much. It doesn't seem like it. So let's do this again. But I've added one more little component here. I've added this 7. So I'm going to take my original, write that down first. And then what I'm going to do is leave it alone and take natural log of both sides. And just like before, what this allows me to do is bring the exponent down. So again, the whole maneuver is to bring this exponent down. So when I bring it down using the power rule for logs, I have the following. So the only thing that's changed from the previous problem to this one is I've added that -7, subtract 7. So what do I do next? Well, that was my result. And I need to continue solving. So one thing I can do, I can either distribute or divide both sides by natural log of 3. I'm going to decide to do this. It just keeps everything clean. So as soon as divide here becomes 1, on one side I have x minus 7, natural log of 5, divided by natural log of 3. And now I'm almost done. So before we would have been done. What's the only difference? Well, I haven't solved for x. I need to add 7 to both sides. So when I add 7 to both sides, I get this, and this is my exact answer. If I want to do an approximation to this, I would just take natural log 5, oops, close parentheses, divided by natural log of 3. Again, notice natural log is a function, that's where you have parentheses. And then I was add 7 to both sides. And there it is. And that makes sense. The previous value was 1.46 something, blah, blah, blah. And this is just adding 7 to that. So it's almost the same as the previous answer, except I added 7 to it. And there you go. So my solution set, again, my exact answer, this is just an approximation, is natural log of 5 divided by natural log of 3 plus 7. So the reasoning here that I've done this is so you can start beginning to see the sequential part aspect of this. You can see that the only thing I've added now is a 7, and you can see how that has altered the final answer and the approach. The approach was exactly the same except for this last step. Okay, so let's continue. Now I'm gonna how is example 8 different from example 7? I've now subtracted. I still have something to the exponent. I subtract 5. I still have a constant in this sign. So now let's solve this one. I do have e, so this is going to make the matter a little easier since I can take in the natural log. But the first step then is to, since here the exponent is my variable, I don't have anything else hanging around this exponential part, I can just go ahead and take the natural log. But I cannot do so right here because I'm subtracting. If I decide to take the natural log of both sides, I don't have an exponential rule that says how to deal with this. So in other words, if I decide to take the natural log and right now, as is, I do not have any rule that says how to deal with this. In other words, I cannot break this up. There's no rule. So my moves are designed to invoke one of the exponential rules. These identities. But this one, I don't have an identity for this. I don't know how to break that up. There is nothing that breaks this up. So what am I going to do then? I'm going to do the same approach as I did before, but it has to look that same look as I have sitting above here. So what's the difference between these two? Is that I'm subtracting the -5. So I need to get rid of this -5. And since this is a term, the only way I can get rid of this -5 is to add 5 to both sides. So I'm going to do that, show that step, so you can make clear that what I am referring to. So this adds up to 0. Here I got -3 plus 5 is 2. And now, see, it looks just like this. And now the steps are identical. So I'm going to take natural log, except this one has a nice little clause. I'm going to take natural log of both sides. And the big difference is I don't need the power rule. I'm not going to use. I'm going to just use the fact that these two are inverses of each other. And then the natural log of e to the x plus 1 power is x plus 1. And on this side, I have natural log of 2. And the only thing left to do is subtract 1 from both sides. And I'm going to just show this step since I have so much room. So then these add up to 0, and I have natural log of 2 minus 1. Notice how much cleaner this looks, and the reason it came out cleaner is because these two are inverses of each other. So I don't have this hanging around, okay? But this little part that's hanging around, you'll notice that thing that's hanging around is the base of the original. So this will always be sitting somewhere in the answer key when you don't change the basis. If you were to change the basis of these two match, all of a sudden you would still recreate this natural log of 3. It would appear, but that takes more work. So instead of using that, we're using the idea of taking the natural log both sides and then exponential rules, not exponential, logarithmic rules or identities. All right, let's finish this last one. Let's solve this, and what have I done differently? Oh, now I'm multiplying by 3. So each time I'm decorating this using transformation. So I've added 7, that boosted up. I'm multiplying here by 3, that stretches it vertically. I'm multiplying by 2, minus 1, so this times 2 here, it's compressing by a factor of half. And this is also being some kind of shift. This is not the shift, but I would have to figure out the shift. Anyway, you can see that I've continued to add a transformation piece to this. So now I'm going to write this here, and this is exactly going to be approach I did earlier. The difference now is I have this 3 here. So the first approach was to isolate, this is where the term of my variable. I'll move everything to the other side, just like I did here. This is my term with a variable. I need to add 5 to both sides to isolate this particular term with a variable. So I'm going to subtract 7 from both sides. And here's the result of that. Got 0 here on this side, and 14 minus 7 is 7. What I'm going to do next, again, I haven't not isolated this term yet with the exponent. I still have this factor of 3, so I'm going to divide both sides by 3 to fully isolate. Could I take the natural log of both sides now? Actually, I could, because now when I do that, there is a rule that says how I can break this up, but it's going to look ugly. So I don't want to introduce taking the natural log until this is completely isolated, like right here. This term with a variable is just a basic exponential minus, of course, at the top here, the exponent is not basic. But I'll do the same thing here, divide, and I get e 2 to the x minus 1 equals 7/3. And that was a little bit remiss here. I'm going to just write this in the final answer. This is my exact answer. And that's what should go there. if you were asked to do a approximation, I said jump the gun with this one. Let me just correct that. I just need to enter this to my calculator. Natural log of 2, subtract 1, and there it is. So this is approximately negative 0.30 and then 69, let's say, when I round to 4 decimal places. All right, so now I come over here, and now I'm ready to take the natural log of both sides. I'm at that position. I've isolated this as much as I could. Everything's been stripped away except the base and the exponent. Now, so in that case, I'm going to take the natural log of both sides. When I do that, these become inverses of each other, and I could just write the exponent. So natural log of e, these are inverses. I just get the input of 2x minus 1. This is just a constant. I'm going to leave it like that. Now I'm ready to solve. This is a linear equation now. This is linear. This is just a constant. So it's like saying 7 or 8 or 9 or whatever, but it's just a constant. So I can add 1 to both sides. And now, because this has a fraction in it, I could, that's okay. That's all right. I'm going to divide both sides by 2. So I divide both sides by 2, and I get this. So don't be tempted to distribute or invite that 2 inside the function notation here. That's not going to work. And this is your exact answer, which of course can be written different ways. I could distribute the half to both of these, and it would look something like this. And of course, because now you're starting to realize there's all these exponential rules, I can continue to massage this a bit, but I'm not going to. I'm going to leave that alone. So the exact answer to this is what you see right there. I like that look, so I'm going to leave it like this. If I want to know an approximate answer to this, I'll just have to enter all this in a calculator. So what I have is, again, 5 times natural log of 7 divided by 3, close it, plus 0.5. And one more time, taking a look. I'm happy that it's 7, it wasn't 3 yet. So there we go. This is the answer to 4 decimal places.